Okay, the question was asked in Piazza to go over quickly the how you handle groups with multiple bonds in double and triple bonds in the Conangle prelog sequence rules to determine R and S. And this would also be true for E and Z. So if we have a carbon, a chiral carbon with a CH double bonded to a CH2 and maybe a carbon double bonded to an O with an OCH3 on this side, maybe an OHCH2 here, and then on this side maybe something like a triple bond with a CH. How would you assign the priorities, group number 1, group number 2, and group number 3? Remember that if you have a multiple bond, what you're going to do is you're going to replace the multiple bond with the multiple number of single bonds. So for instance, when we have this carbon double bond, it only has 3 groups attached to this carbon, and I can't fairly compare that to this carbon, which has 4 groups. And so the reason why I have to come up with what's called an equivalent structure is because I can't compare the 3 groups to the 4 groups here. So what I'm going to do is I'm going to write that exact structure out, only I'm going to leave out the double bond. And now what I'm going to do is I'm going to replace the carbon-carbon double bond for this carbon that I've circled with 2 carbon-carbon single bonds. So this is carbon-carbon single bond number 1. I need to add an extra carbon in, so now I have my 2 carbon-carbon single bonds. On the other side, this carbon I'm going to put in a square, it also has a carbon-carbon double bond, and so I'm going to replace it with 2 carbon-carbon single bonds. So again, here's the first carbon-carbon single bond, and there is the second. So this would be the equivalent structure of a carbon-carbon double bond. For this carbon right here, which is the one that's going to be attached to the chiral center, that means that carbon now has 2 C's and an H attached to it. For this carbonyl, let's do the same thing. So I'm going to write the structure of that out without the carbon-carbon double bond. Now I'm going to replace this carbon-carbon double bond with 2 carbon-carbon single bonds. So here's the first one, and here's the second one. Then I have to look at the other atom that's involved in the multiple bond, and in this case, the oxygen, it has a double bond to the carbon, so I'm going to replace it with 2 oxygen carbon single bonds. So here's the first one, and then here is the second one. So this would be the equivalent structure of that ester. This carbon now has 3 O's attached to it. Over here, there's nothing to worry about. That carbon doesn't have a multiple bond, so it has 2 H's and an O attached to it. And then up here, the carbon-carbon triple bond, I would write that carbon-carbon triple bond without the triple bond, and now replace for this carbon right here, the one that's attached, I have a triple bond, so that means I need 3 carbon-carbon single bonds. Okay, carbon-carbon single bond number 1, number 2, number 3. This carbon over here that I will put in a square again has a carbon-carbon triple bond, 1, 2, 3. And so this would be the equivalent structure of the triple bond. This is the carbon that's attached over here to the chiral center, which means that carbon has 3 C's attached to it. And so now, determining groups 1, 2, 3, and 4, I'm going to look at the carbon-carbon double bond, which is 2 C's and an H attached to it. Down here, this carbon has 3 O's. this carbon has 2 H's and an O, and the carbon-carbon triple bond has 3 C's. So in terms of priorities then, the groups with the oxygen have a higher priority than the groups without. In this case, 2 H's and an O is not beating 3 O's, so 3 O's would be number 1. The oxygen present gives precedence or preference over the 2 carbons that don't have any oxygen attached, because remember, it's the single atom that has the highest atomic number. So this would be group number 2. And then comparing 3 C's versus 2 C's and an H, the 3 C's would get group number 3, and then the 2 C's and an H would get group number 4. So we always write out the multiple bond. So if we have X multiply bonded to Y, we write the structure out with the single bonds, and then we give each atom a multiple number of single bonds. So in this case, this would have a Y group attached, and over here it would have the X group attached. And of course, the Y group would have 2 bonds, and the X would have 1, and those groups would still be there. Okay, so hopefully that makes sense. That's just a quick refresher on how to handle the equivalent structures of multiple bonds when you're doing Kohn-Ingold pre-log sequence rules, which is what you do for RNS, but you would do the same thing if you wanted to determine E and Z. Okay.